All right, perfect. All right, so I hope that you've been keeping up so far in terms of like normal groups, cosets, these sorts of things, because this lecture is a doozy, right? Like period, there's kind of no two ways about it. Which is why I think that we took so long once we started introducing cosets in order to actually get to this topic, right? Which is the natural context in which you set up cosets, which is to talk about quotient groups. Now, I think for many of you, this might be your first time ever seeing quotients. If you've taken 224 or 240, there's a possibility that you've seen vector space quotients in that case, and group quotients are very, very similar. They're effectively the same. But if not, then this is your first experience in quotients, and it does take a little bit to wrap your mind around. Okay, it's a little bit tricky. So I am going to take a slightly different approach than the book. Okay, and not that there's anything wrong with the book, but just because I want to give you as much exposure to different things as possible. And so what that means is that if you don't like the book's treatment of it, maybe you'll like the treatment that I'm going to do, and vice versa, right? If you sit here and at the end of this lecture, you're looking at this and you're like, what the hell just happened? Then you can go and read the book or look at Ali's lecture as well, and you'll have a different perspective. We're going to talk about the same things. We're going to prove the same things. I'm going to attack it from a different perspective, again, just to give you those options, right? And if you remember, when was this? 3 weeks ago? I think it was November 1st. It was the lecture we had November 1st. It was the first time we were talking about cosets at all. And I introduced these two propositions, right? And let's take a second to read through them and remind ourselves what these were saying, because I alluded at that time that this would be important when we talked about quotients. So now is the time we're going to talk about quotients. Let's look at them and, assure ourselves or remind ourselves what they are, because I'm going to lean on these somewhat heavily. So these are actually two directions of an if and only if theorem. And I'm going to write that if and only if theorem down in a second. The first proposition says, if I give you an equivalence relation on your set G, on your group G, and it satisfies this special property, okay, A is related to B, then GA is related to GB for any G and G, then we have two things. We have that the equivalence class of the identity is a subgroup of G, and that A is related to B if and only if A inverse B is in that equivalence class of the identity. And I've put it in green here, but really it should be yellow. That's equivalent to saying that AH is equal to BH, right? And so another way to say this part right here, part 2, is to say under this equivalence relation, the cosets of H are precisely the equivalence classes. Okay, so the cosets of H are the equivalence classes. Okay, so if you're given an equivalence relation on G that satisfies this special property, then taking your subgroup to be the equivalence class of the identity gives you that the cosets are the equivalence classes. And again, if you look at that blue rectangle, that is a very natural thing to demand, right? That if A is related to B, then GA is related to GB. This is somehow a compatibility condition, right? Because you could put whatever, when we put an equivalence relation on a group, you're really just putting it on the underlying set, right? There's no notion of how that equivalence relation interacts with your binary operator in any way, shape, or form, right? It doesn't have to interact with your binary operator. So saying that GA has to be related to GB is saying that, look, that equivalence relation, is compatible with your binary operation. If you multiply two equal things, right, where you're saying like A is equal to B here, if A and B are equal, then GA should also be equal to GB. Right? Like that's a very natural thing to ask, that your equivalence relation be compatible with your group operation. Okay? So that's one direction. Now, proposition 2 is the converse. It says that if you give me a subgroup, right? So in the previous one, we started with an equivalence relation and from that got a subgroup. The second proposition says, if you give me a subgroup this time, then you can define an equivalence relation on it. And in that case, the equivalence classes are again the cosets. Okay, and it satisfies, not only is it an equivalence relation, but it does satisfy this special property as well, right? That if A is related to B, G of A is related to G of B. Okay, so these are two sides of an if and only if. And if we wanted to, what we could say is that maybe I'll state this as now a third proposition for which the proof is the first two. So proposition, if G is a group, there is a bijective correspondence between subgroups of G and equivalence relations which we call, tilde here, such that if A is related to B, then GA is related to GB for all G in G. Okay? So we've said there's a bijective correspondence. Injectivity is one proposition, surjectivity is the other one. Or if you want, the forward direction, you define a map, you define its inverse. One of these gives you the forward direction, one of these gives you the reverse direction. Okay, so there's a bijective correspondence between subgroups of G and equivalence relations such that this property is true. You can imagine, so this corresponded to left cosets, right? We said if in all of these cases, the equivalence classes with a collection of left cosets. I guess we really should be a little bit more clear about that. Let me put left cosets right there, okay? Now, all you have to do to make it right cosets is to change it from being GA is related to GB to being AG is related to BG, okay? So all the theorems above, so note, I guess they were propositions, all the propositions above hold if we replace. So what we're going to do is we're going to replace A inverse B in H. That's going to become A B inverse. We're going to change the word left coset to right coset. And we're going to change I might need some more space here. A related to B implies GA related to GB. We're going to replace that with A related to B implies AG is related to BG. Okay, so everything we did above was related to left cosets, but if you make the corresponding changes, the theorems are all exactly the same, but now for right cosets. So mutatis mutandis, you change the things that you need to change, and you get the exact same results for right cosets. Okay, so that's a nice sort of thing. Obviously, there's the symmetry between left and right cosets, and that's what we expect. Okay, now, 2 weeks after we did this lecture, we started talking about normal subgroups. And we said normal subgroups are really the thing that we're going to need, right? Like when we take quotients, it's going to have to be by normal subgroups. So why normality? Why is normality the important thing? And the reason for that is the following theorem. Again, this is going to be very similar to what was proven in the book, but is a little bit different because we're going to phrase it in terms of equivalence relations rather than in terms of cosets, but then I'll retranslate it back into cosets for you in case you need something concrete to work with, okay? So as far as I'm concerned, this is a major theorem, okay? And it goes as following. So let me just double check what I want to say. So let's say fix an equivalence relation. Tilde on G, okay? And let pi map G to G tilde, which takes little g to the equivalence class of G. Are you all familiar with this notation? Have you seen what G tilde means before? Is that like completely new, or are people confused by that? I feel like that would have been defined in Math 102, but I could be wrong. You're confused? Okay, yeah, so you've never seen it. So G mod tilde here, let me just maybe put this onto the side. So G mod tilde, this is just the notation that we use to say this is the collection of equivalence classes. Okay, so G mod tilde is the set of equivalence classes. Okay, does that make sense now? Right, because you've got an equivalence relation. You know that if you have an equivalence relation, you then have a corresponding set of equivalence classes, right? Where you just take the set of all things that are related. You pick an element and take all the things that are related to it, and that's an equivalence class, right? So G mod tilde is just the set of equivalence classes. And then what pi is, it's what's called a quotient map. It just takes an element and maps it to its equivalence class, right? So you've probably been doing that left, right, and center all of the time. It's just you didn't write down a map which actually did it, but it says, give me an element, and then I will send it to its equivalence class. So does that make sense? Does everyone, right? Like maybe the notation is a little bit freaky here, but don't be freaked out by it. It just says, take an element, send it to its equivalence class. That's okay? Okay, cool. Right. Same thing. Like if you imagine if you took the integers and you map them to the integers mod 5, what would you take 7 to 2, right? Because 7 is congruent to 2 mod 5. So you're just mapping the set to its equivalence class, right? So that's exactly what we're doing. So let's let this be the quotient map. All right, back to green. So now we want to say the operation defined, let me say defined as. Now let's give it a name. The operation dot defined as A dot B. That's pi of A dot pi of B. Okay, so there's no note. I haven't actually defined what this thing is going to do yet. I'm just saying, look, I can write the equivalence relation of A as pi of A, right? Because that's what pi does. And now here's what it's actually defined to do. That's going to be pi of AB. Okay. And what you can see is that I'm basically setting this up so that pi is going to be a homomorphism, right? Because that property between the second and third part of the equation, that is precisely what it will mean for pi to be a homomorphism, right? So I'm defining this group operation in such a way that pi is a homomorphism. So this operation defines a group structure on the set of equivalence classes if and only if whenever A is related to B, then GA is related to GB, and AG is related to BG for all G and G. Okay, in this case, the equivalence class of the identity is a normal subgroup of G, and pi is a homomorphism. Okay, so there's a lot kind of going on there, but what we're saying is we want to take the collection of cosets, which we know are the equivalence relations. We want to take the set of cosets, we want to turn them into a group. And you might say, well, maybe there's many ways of doing this. Like why did we want normal subgroups? Why is normality the important thing? And this is the reason why. It is the thing which turns the quotient map that you have just on the set level and turns it into a group homomorphism. Okay, so that's why it's the natural thing to do. Because yeah, again, you could say, well, why don't, what's forcing us to use normal subgroups? Why couldn't I just put, and again, you might not see quite how normality comes into this yet, but why couldn't we just find a different structure? Well, we want this map to be a group homomorphism. We want, if you take an element of the group, and map it to its equivalence class, that is a group homomorphism, right? That's why we do this. Okay, now there isn't much to prove here because from what we have, well, listen, we're basically going to use the previous proposition, this fact that there is this bijective correspondence between subgroups of G and the equivalence relations which do this thing, right? We're basically just going to use that. Okay, so let's see. And by the way, here's where normality comes from, right? It's going to come in right here because both of these things have to be true at the same time. That's the same thing as saying that you're both, your left and right cosets agree, right? Because again, we talked about the equivalence relation, the equivalence classes are cosets, and then the thing on the left are the left cosets, the thing on the right are right cosets. So requiring that both of these conditions be true, we'll also guarantee that our left and right cosets coincide. Okay, so the proof of this fact is very, very quick. So let's go in the forward direction. Okay, so what are we trying to prove again? So we've got an if and only if. So we're going to assume that it defines a group structure and prove that the equivalence relation must satisfy GA is related to GB and AG is related to BG. Okay, so suppose we have a group structure. Okay, so in particular, this relationship, the dot relationship that I've defined here, maybe let's give this a name. The dot relation that I've done in star here is well defined, right? It has to be well defined. It's an operator on equivalence classes. So we have to make sure if I chose different representatives, I'd get the same elements, right? Well, we're told it's well defined, right? We're told that it's a group operator. And we know if you go way back and remember like very chapter 1, the stuff that we did in the first week, we talked about what it meant for a binary operator to be well defined, right? So what does that mean? So that means that if the equivalence class of A is equal to the equivalence class of A prime, and G is some other equivalence class, then we have to be well defined in each of our components separately. So that means that A dot G is AG. That has to be equal to A prime G, which is A prime G, like that. Okay, but if we translate what this means and what this means, that says that if A is similar to A prime, then, right, so that's kind of the yellow part, or maybe let me use different colors here. All right, so this is the yellow part. Then AG is related to A prime of G, all right? And that's the blue part. And that's one of what we wanted to show. And I'm going to say, like, if you do the same thing without me actually explicitly writing it out, you can check it if you want. But if you also check well-definedness in the second component, it obviously gives you the other thing, right? It gives you AG is related to BG, right? So checking well-definedness in the second component gives A related to A prime implies GA is related to GA prime. Okay, so that's the forward direction. That's why we require both of those things to be true at the same time, because we have to be well defined in both of the components of our binary operation. Okay. So if we only assume left cosets, basically, if we only use left cosets, we only get that we're well defined in the left of our binary operation in the first component. And then we need to use right cosets in order to get well definedness in our second component. Okay. And now in the other direction, suppose that our binary operation satisfies those things. Well, it's clearly well defined. Suppose A related to B implies GA relates to GB, and AG is related to BG for all G and G. By the same proof that we did above, we're well defined. By the forward direction proof, the operator is well defined. Right? The operator is clearly associative. And I mean, I say clearly, but maybe let's just write it out. But you're going to be like, oh yeah, this is stupid. Obviously it is. Once I write it out. Right? So we want to show that I can re-bracket this. And well, the binary operation just basically smushes the equivalence relations together, right? So that's going to be AB dot C like that, which is going to be ABC. But we know that the binary operation is associative in the group. So I can certainly write this now as ABC, which is A dot BC, which is A dot B dot C like that, right? So there's a whole lot of algebra to not show anything. As far as I'm concerned, and I know that some people here have actually taken 224 with me, and in those cases, as well, I say like, this just follows clearly from associativity of the group, right? The kind of, where did we really need to prove something? Well, it was right here, but that's obviously true in the group. So it's obviously true in the cosets as well, right? In the collection of equivalence relations or equivalence classes. So I would be fine if you just said associativity is clear. The identity element is the equivalence class of the identity. Right, so we claim that the equivalence class of the identity is the identity. And again, what is there to prove? Because if you take the identity acted on G, that's the equivalence class of EG, which is just the equivalence class of G, right? And then inverses, well, again, it's the obvious thing, right? The equivalence class of G inverse times the equivalence class of G is going to be the equivalence class of G inverse G, and that's the equivalence class of the identity, right? So you're done. So you have a well-defined group operation. Okay. So this is a very kind of like, this is a fairly abstract statement. There's no doubt about that. But the beautiful thing about this is, I guess I should prove that E is normal. Okay, I'm not going to prove that pi is a homomorphism because there's nothing to prove, right? The fact that pi is a homomorphism is precisely this statement right here, right? That's what it means to be a homomorphism. So we don't need to prove that pi is a homomorphism. That's immediate, but we should prove that E is normal. Okay, so let's prove that E is normal. Okay, so so we know that the equivalence class of E, let's give it a name so we don't keep calling it the equivalence class. So we know the equivalence class of E is a subgroup. Of G, right? That was part of the very first proposition, is that the equivalence class of the identity was a subgroup. So now we want to show it's normal. So fix some element G in G. Okay, so if G is related to E, what does that mean? So that means that G n is equal to n, but it also means, because we have that this is both a left and a right coset representative, we also have that NG is equal to n, and the combination of these things tell us that Gn is equal to n is equal to ng, and this is one of the things that we said was equivalent to n being normal. Right? So n is a normal subgroup of G. Now we're done. Okay, and so again, just to remind you, right, when we write this down, So almost like I didn't need to use cosets until this very last part, right? Like right until here, I didn't actually use cosets at all, but just as a reminder, right? So we have the equivalence class of G can be written as either the left coset or the right coset. Okay, so you can think of this as being, right, because this is exactly the principle of normality, but by what we did above, we said the equivalence classes are precisely the cosets. So you can think of it like this. And then in that case, if I do something like G1 dot G2 is equal to G1, G2, then at the level of cosets, this means I'm saying G1n times G2n is equal to G1, G2n, right? So this is how that dot operator is defined, is it says choose, two representatives of your coset, and then kind of ignore the end part and just multiply them together and then take the coset, right? So you take G1n, you take G2n, and then you multiply G1 and G2 together. It's kind of like the n is just coming along for a ride, right? So it's not super important. It's just coming along for a ride, but it has to stay consistently in here because we are looking, right? We're defining the cosets of n as a group. Okay, so that's what's actually happening on the coset level. If you want to translate this from equivalence classes to cosets, this is exactly what's happening. Okay. So are there any questions about that? Excuse me. Let me maybe zoom out here again. And you're probably starting to appreciate that, yeah, understanding what quotients are is a little bit tricky, right? It can take some time to understand what's actually happening. But there's a nice picture that we can employ. And I think that thinking about things this way is really, really powerful and is really, really good. So let me try and give you a little bit of geometric intuition, because I suspect by now, right now, your brains have already fried out, right? Like we're 30 minutes into the lecture and already there's smoke coming out of your ears. So let me kind of give you a picture of what we're doing. So you remember in the past, especially when we were talking about Lagrange's theorem. So here, let me say that this is kind of like a nice geometric picture. Okay, so when we were talking about Lagrange's theorem, what I would do is I'd kind of draw the group as a rectangle, right? I kind of do it like this. And then I'd say, oh, your coset is, is a box in here, but maybe let me just write a coset like this. Okay, so this blue line is the coset H, right? And then maybe, for every single blue line, right? So for every vertical line, you've got a different coset, right? So this might be like G1H here. And this coset here, this vertical line is like G2H or something, right? So basically, you've got all of these vertical lines, and I've only drawn 3 of them, but in this case, there's actually infinitely many. What the quotient does is it takes each of these blue lines and it goes, okay, and it kind of shrinks them down to a single point. So it chooses some point to represent that whole line, right? And then what you could do is if you say, well, like if I shrunk all of these blue lines down to a single point, what's left over? Or maybe let me do that in a different color, right? You get the green thing, and the green thing is G mod H. Right? So you've taken each of the blue lines. And again, you can hopefully you can visualize this. Does everyone see the picture? So you've got this 2-dimensional shape. And if you write it as just like all of these blue vertical lines, like you took a union over all of these blue vertical lines, if you were to shrink all of these blue vertical lines down to a single point, then what do you get left over? You just get kind of like this one horizontal line, right? And what we're saying is that if your group H is normal, then you can actually define a group structure on the green line, the green horizontal line, that is compatible with the blue lines, right? And what does compatibility mean? It's again precisely that the projection map, the map which takes everything in the blue and maps it down to its single point representative, that's actually a group homomorphism. Okay? Does that kind of make sense? Are people okay with that? Okay. Is anyone bothered? Let's do an example. Maybe an example will help. Okay, so as an example, so let's take our classic example, and you might have actually seen this, especially if you've done any Googling or looking up additional resources for this class. So let's be concrete. Let's actually choose 5z, right? So 5z is the collection of integers that are divisible by 5. So for example, ... -10, -5, 0, 5, 10, ... right? So this is a subgroup of Z. And in fact, it's a normal subgroup, right? Maybe let's draw it as a normal subgroup. And we know it's normal because Z is abelian, right? And we said earlier when we were talking about normal subgroups, every subgroup of an abelian group is normal, which means that we should be able to take a quotient by it, right? Because we can always take quotients by normal subgroups. So let's take a look at it. So we know, therefore know, that Z mod 5Z, and we know exactly what the cosets of this are. If you go back and you look at the first day that we ever talked about cosets, we did one that was similar to this. I think we might have only done Z, like 3Z there instead of 5Z, but it's the same sort of thing. All right, so here are the cosets. And it's got 5 cosets in it. We know that this is a group. And our operation is this. So we're going to take A plus, 5Z. Damn it, I should have put 5Zs everywhere. So we get 5Z, 1 plus 5Z, 2 plus 5Z, 3 plus 5Z, 4 plus 5Z. And our relationship is just to add the things in front, right? So we get B plus 5Z is equal to A plus B plus 5Z, like that. Okay, and if you think about it, this is one clearly cyclic. All right, this is cyclic since A plus 5Z, you can now get that just by adding 1 plus 5Z to itself A times. Right? So that means that Z mod 5Z is generated by 1 plus 5Z, like so. And more importantly, it's a cyclic group of size 5. We know those things are all isomorphic. So Z mod 5Z is isomorphic to Z5, right? The group of integers mod 5. And this is, again, I don't think that you're surprised by this. I mean, you probably have seen this notation. Some people use Z sub 5 to indicate this group. Some people use Z mod 5Z. And the reason is those are really the same thing, right? In fact, if you think about it, right, if you really want to get deep and dirty into this, look at something like 2 plus 5Z, right? Oh, in fact, if you want to, we can explicitly write out the homomorphism here. So it's phi maps Z5 into Z mod 5z. And the homomorphism takes the equivalence class of K and maps it to the equivalence class of K plus 5z. Or let's just say K. Right, so it's an obvious isomorphism. And in fact, what I'm saying is if you take a look at 2 plus 5z, if you write this out, what is it going to be? Dot, 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 -8, -3, 2, 7, 12, dot, dot, dot. These are precisely the set of things that have a remainder 2 mod 5, right? So these things have a remainder of 2 mod 5, right? And that 2 comes from here. So you can imagine that if you have K plus NZ, those are just the collection of all integers that end up giving you a remainder of, what did I say? K plus NZ, give you a remainder of K mod N, right? So it's a very nice correspondence between this quotient group and what we would normally think of as being the equivalence classes under modular arithmetic. Okay, so that's pretty nice. That's a nice thing to think about. What else do we get? Oh, immediate corollary. This is a nice one too. And I can't remember who asked it last time, but you'll remember somebody last time said, okay, listen, how do we prove that groups are normal? And I said in that lecture, I said, actually the number one way that you can prove that groups are normal is to demonstrate that they are the kernel of a group homomorphism, right? Because we proved that kernels of group homomorphisms are normal. I was asked, how do we prove that groups are normal? I said, well, actually show that they're a group homomorphism. And we did something like that on Thursday, right? Where I showed that SL2 was normal in GL2 by showing it was the kernel of a group homomorphism. So corollary, if G is a group, then N is a normal subgroup. N is normal in G if and only if there exists some map phi G to G prime, a group homomorphism such that N is the kernel of phi. Okay? And one of these directions we've already proven, right? So what this says, like if you think about this for a second and you read what this says, it says that there is a perfect correspondence between normal subgroups and kernels of group homomorphisms, right? Every normal subgroup is the kernel of some group homomorphism, and the kernel of every group homomorphism is a normal subgroup, right? So there's this perfect correspondence between normal subgroups and kernels of group homomorphisms. Now we've already proven one of these directions, right? Which direction did we prove? We've proven this one. Already proven, right? So that direction says if you're the kernel of a group homomorphism, then you're a normal subgroup. We proved that, whatever it was, last week when we were talking about, normal subgroups. The forward direction is just one line. So now let's suppose that you're normal, right? And we want to figure out, what are you the kernel of? Note that if pi mapping G to G mod N, okay, and that, right, G mod N here is the same thing as G mod, the equivalence relation that I had above. Those are the same thing because we said the equivalence classes are precisely the cosets, right? So if pi mapping G to G mod N is the quotient map, right? Well, let's look at this thing's kernel, and you can probably guess what it's going to be. So the kernel of pi, well, what is it? So it's going to be the collection of all elements of G such that Gn is equal to N, right? Because this thing here, this is pi of G. This thing here is the identity in G mod N. Right? Okay, and what elements of the group G satisfy Gn is equal to n. Well, when we were first talking about cosets, we said, well, this is only true if little g is in n, right? So this is precisely the set n. And that's what we wanted to show, right? We wanted to show that n was the kernel of a group homomorphism. It's naturally the kernel of its own quotient map, right? So you know that it's a normal group. You can take G mod n. There's a natural homomorphism from G to G mod n. N is the kernel of that group homomorphism. Like so. Okay. So that's nice. And in some sense, you'd be like, okay, well, this is kind of stupid. I mean, okay, if I want to show that a group is normal, I need to show that it's the kernel of a group homomorphism. But the way that you prove this was to take the map from G to G mod n, which we only know is a group homomorphism if we know that n is normal in the first place. So that seems a little bit circular. But again, if you look at what I did, like this is a candidate map. It's not the only possible one, right? So this is a map for which n is the kernel, but there could be multiple. There could be many other such maps. And that's the power of it. So yes, I can prove it using this particular map, but there could be other ones. And again, if you want to see an example of that, go back, look at what we did just on Thursday, where I showed that SL2 was a normal subgroup of GL2 using a kernel of a group homomorphism. And that'll give you a good example right there of something else, okay? Because we didn't, in that case, we did not definitely map from GL2 on quotient SL2. We didn't do that, right? Okay, any questions so far? Is everyone okay? I think probably some brains are hurting, but that's okay. All right, this is fun stuff. I really like quotients. They do take a little bit of time to get used to, though. Okay, like I said, if you're feeling a little bit confused at this section, that's totally all right. That is totally normal. Everyone is confused when they first see quotients. But you have to play with these things, and you have to play with them a lot and play with them well before things really start to settle in. Okay. Let's do, what am I going to do next? Oh, here's a theorem. This theorem is proven in the book. But it's a nice one because, again, it gets us to, play with quotients a little bit. So I kind of want to do it for that reason. So suppose n is a normal subgroup of G, and that G mod n is cyclic, and n is in the center of G. Then G is abelian. Okay. So that's nice. Let's see. What I want to try and guide you through is, let's say I had asked you to prove this. There's a lot of stuff going on here, right? Principally, we have actually 3 hypotheses, and most theorems that we get don't have 3 hypotheses. So what are our hypotheses here? We have that n is normal, okay, important hypothesis. We have that the quotient group G mod n is cyclic, and we have that n is part of the center, right? So we expect quite reasonably that we're going to have to use all 3 of these things in order to do our proof. Now, when there's 3 hypotheses especially, and we're in 3rd year now, so there's an expectation that we can start to ask harder questions. When there are 3 hypotheses, I think it becomes very easy to become overwhelmed with what you're being asked to do. So let's take it slow and let's think about what exactly it is that we'd be trying to show. All right, so proof. All right, so what do we want to show? We want to show that G is abelian. So let's choose 2 elements of B, right? Let A and B be elements of G. We want to show that AB is equal to BA. Okay, I've done nothing, right? I haven't done anything here. The only thing that I have done is just written down what the definition of abelian means, right? So we want to do something like this. We want to show that AB is equal to BA. Okay. And now you get stuck, right? And you're like, what the hell do I do next? So we look at our list of 3 hypotheses. Anytime you're stuck, take a look at your hypotheses and say, okay, what haven't I used yet? I probably can't use the fact that n is in the center of G yet. That's not going to do me any good because I don't know how A and B might be related to n. Same thing, n being normal is not useful. But what strikes me here is G mod n is cyclic. Okay, I don't know how that's going to help yet, but at the very least, what it suggests I should do is look at G mod n. And again, I can push A and B into G mod n, right? So let's look at the equivalence class of A. So let's look at the equivalence class of A and the equivalence class of B in G mod n, right? So that's what I'm thinking. Now I can use the fact that G mod n is cyclic. So since G mod n is cyclic, there is some C, let's say in G, or you could say equivalence class in G mod n if you want, such that G mod n is generated by the equivalence class of C. And so there exist M and N in Z, such that the equivalence class of A is the equivalence class of C to the N. That's the same thing as C to the N, like that. And the equivalence class of B is C to the M. And of course, we can put the M inside like so, right? Okay, so somehow, great, I've used that second hypothesis. I've used the fact that G mod n is cyclic. And now I've been able to write the equivalence class of A in terms of C. And I've been able to write the equivalence class of B in terms of C as well. Now, at this point, you get a little bit stuck and you're like, okay. So I don't want to work in the quotient group because I need to say something about A and B, not the equivalence class of A and B. So let's see if I can go back. Let's see if I can exit the equivalence class notation and return to the group. And the way that you're going to do this is, well, let's translate this notion of equivalence classes back into cosets. All right, so I'm going to say that is A is in C to the N, N, and B is in C to the M, N, right? Because that's what it means for these two things to be in the same equivalence class, right? Remember, the cosets are the equivalence classes, right? That's the important thing. The cosets are the equivalence classes. So I've got A is in C to the N, N, B is in C to the M, capital N. So there exists N1 and N2 in N, such that A is C. Maybe let's not call them. Oh, no, okay. N1, C to the N, N1. I should have used a different exponent instead of N there. But it's okay. It's not the end of the world. Like that. Okay, so A is C to the N, N1. B is C to the M, N2. Perfect. I've now been able to, right? So I pushed down into the quotient, G mod N, use cyclicity there, and now I've risen back up, back from the quotient and equivalence classes, and now there are no equivalence relations anymore, right? I've got A is equal to something and B is equal to something, no equivalence relations whatsoever. Now is a good time. Let's multiply A and B together. Multiplying gives, so we've got AB, CN, N1, CM, N2 like this. And then again, here you get stuck, but you say, there is a third hypothesis that I have not used yet. And that third hypothesis is this third one at the top right-hand corner, which says that N is part of the center of G, namely N commutes with everything in the group, right? So if N commutes with everything in the group, what I'm going to do is I'm going to take N1, I'm going to put it over here. So that's going to give me C to the N, C to the M, N1, N2. Now, clearly, these two things commute with each other, right? So I can flip them around. C to the M, C to the N. Again, these two things commute with each other as well because they're both in the center. So I'm going to flip them around. And then finally, I'm going to use the fact that N is in the center one more time to push the N2 over. And hopefully you see what I'm trying to do here. There's just a whole bunch of like stupid little algebraic moves, but what I've done with enough finagling, enough pushing stuff around, is I've managed to reconstruct A times B, but now in the opposite order, right? I've got B first and then A. So, and that's what I wanted, right? I've now shown that A and B commute. And since A and B were arbitrary, G is abelian. And so I'm done. Okay. Now, this is an important point. There's a lot of things to take from here. Not only the fact that this is something that probably looks scary, but again, in some sense, it had a natural progression of how you should have looked at it. But more importantly, what it really illustrates is how you can use information about the quotient to give you information about the original group, which is a weird direction, right? Normally, we're totally okay with the idea of pushing information from the group down onto a quotient. That doesn't seem like that should be a crazy thing, right? If you know lots of information about G, then when you go and shrink stuff, you probably know some information about the shrunk stuff too, right? That's not crazy. You go from lots of information to restricted information. That seems reasonable. The thing that's a little bit crazier is that we can partially go the opposite direction. Of course, we needed a lot more hypotheses here, right? We needed a lot more stuff. But with enough information, we can actually go the opposite direction. We can take information about the equivalence classes and extrapolate some information about the ambient space, the group G from which we came. So that's number one. Number two is specifically the technique of how do you go from the equivalence class back up to the group, right? So what is that specific technique? And that specific technique is right here. Okay, let me highlight this in red. All right, that's what I did right here. Okay, so this is how you go from talking about G mod n. So how you go from talking about the quotient to how you go to talking about G. Right? You don't have to do any sort of weird thing and talk about pi inverse. Don't talk about pi inverse. That map is not invertible. It's super not invertible, right? But it doesn't matter because you can choose representatives, right? Shouldn't be a crazy thing to you. You've probably done that before when you play with equivalence relations. You say choose an equivalence class, let's choose a representative of that equivalence class. And that's effectively what we're doing, right? When I did this, I was saying, let's choose a representative of the equivalence class so that I could work in the group again, right? Instead of working in the quotient, let's work in the big group. Okay, so that's important. And I want you to think about like what we did there. And, you know, because you're going to be asked to do these sorts of things plenty of times on your own in the future. Okay, so that's kind of something important to keep in mind there. Okay, are there any questions so far? This is probably a natural breaking point. Let me just give you my ballpark for where we're headed. I think I'm going to do one more example using quotients, and then we'll talk about the isomorphism theorems. And I think I'm going to prove 1 and 3. I'm not going to prove 2. The book has the proof of 2. It also has the proof of 1, which we can just talk about quickly. There's a really slick proof of the first isomorphism theorem, but I realized I'd have to prove a bunch of other things if I really wanted to do it. Yeah, so I will prove for you for sure the third isomorphism theorem. That is something that we will use. And I, again, will give a slightly different proof than the one in the book, just to give you another different perspective. But yeah, that's the plan. That's the game plan. Okay, so are there any questions about this stuff? Everyone's happy-ish? Happy-ish? Okay. All right, then. So let's break for 10 minutes. So I've got about 4:08 or so. Or sorry, not 4:08, 2:08. So I've got 2:08. Let's come back at 2:18 or about 10 minutes time. If you have any questions in the meantime, please don't hesitate to throw them in the chat. I know this stuff can be confusing, okay? And I want to try and clarify any confusion that you have sooner rather than later. So if you have any questions, throw them in the chat. I will address them. We might even talk about it a little bit when we come back, if it warrants it. And yeah, that's it. So, okay, so we'll talk in 10 minutes. I'll see you then. Okay, we are back. A little bit of quotient groups. We're going to continue. Okay, so for this one, let me actually, I have to recall something. This one is a little bit, here's a nice little exercise. I really like this one. It's kind of interesting where this shows up. So exercise, so recall that if G is a group, then we defined this thing. Do you remember this? I think, when did we do this? This was last Tuesday, so it was a week ago, right? And this is the subgroup generated by G inverse H inverse, as G and H were allowed to vary over the group. Okay, so you would take these sorts of words like this, right? And then you take the subgroup generated by all possible combinations of all possible finite combinations of these things. And last time we actually proved that that was normal, right? Inner group G, it's always normal. And one of the ways that we did this is we looked at the inner automorphisms, and we showed that the inner automorphisms preserve something that we call the commutator. And if your inner automorphism group perfectly preserves your, if your group is always preserved under every inner automorphism, then it's, in particular, it's normal. Okay, so last time we proved that that is a normal subgroup in G. Now what we want to prove is that G mod GG is abelian. Okay, and so that's a cool thing, because if you start out with an abelian group, then this GG thing, this commutator subgroup, is trivial, right? Because G inverse H inverse is just always the identity. So if you start out with an abelian group, then G mod GG is just G. So you just get back the group itself. The interesting thing happens if you don't have a commutative group, right? If your group is non-abelian. So in that case, your commutative subgroup is non-trivial, right? But you're still guaranteed that G mod the commutator subgroup is abelian, right? And in some sense, there's a sense in which it is the best abelian approximation to your group. So this thing is, not only is it abelian, it's called the abelianization of your group. Maybe we'll put that as a comment. So G mod GG, so sometimes this is written as GAB like this, is called the abelianization. Okay, and again, you know, if you want to pursue this, there's an interesting way that you can do it, but you can show that basically this is the best abelian group which approximates G itself. Okay, and this, I think, looks terrifying, right? Like this looks like a really complicated sort of question, but it's actually almost trivial. Like there's almost nothing to do. Okay, so proof. So let's suppose that we have two equivalence classes. All right, so let's say that let A and B be in G mod GG, like so. All right, so what do we want to show? We want to show that A dot B is equal to B dot A, right? Now that's the same thing as saying AB is equal to BA, right? Where we actually just act out what the group operation is. And then in particular, because I really want to use this fact that I know what the commutator subgroup looks like, let's put the BA on the other side, right? So I really, that is the same thing as showing A, B, A inverse, B inverse is equal to the identity equivalence class, right? But now if we translate what this means, so translating this last equality, what it means is that it suffices to show that A, B, A inverse, B inverse is in, well, what is the equivalence class of the identity? It's precisely whatever the normal subgroup you're quotienting by. So it's enough to show this, right? But this is trivial. That's pretty much the definition of the commutator subgroup, right? This is definitely one of the generators of the commutator subgroup. But this is trivial, right? So we're done. So effectively what's happening there is when you compute the commutator subgroup, what you're doing is you're really looking at all the possible ways that you can combine things in a non-abelian way. And then what you're doing is just saying, I'm going to take all those things, all the non-abelianness, right? That's what the commutator subgroup is capturing. It's all the ways that your group can fail to be abelian. And then when you quotient by it, remember what I said, you go, right? So you take all those things and you treat them as a single point. And in particular, you treat them as the identity. So now when you quotient out by the non-abelian things, you're treating all the non-abelian things as the identity. Well, what's left over? Well, what's left over has to be abelian, because if you're abelian in the original group, once you get rid of all the non-abelian stuff, the stuff that's left over is abelian, right? So that's effectively what's happening here with this abelianization. And again, there's other things you could do. You could always argue that G mod G, right? If I take the G is certainly normal in itself, and if I take the quotient of G with itself, I get the trivial subgroup, right? I just get the identity coset. That's abelian. Why don't we define that as being the abelianization? You might say, as a snarky answer. There's something called the universal property, which basically tells you that this is the best thing that does it. I don't want to tell you what universal properties are, but if that's something that's interesting to you, you can go up, you can look up abelianization, and perhaps in particular, you might need to put in universal property there, and it will tell you that this is actually the best abelian approximation to your group, basically. Okay, so that's kind of like a fun little thing. This is a question I think looks really, really hard, is not in any way difficult, right? You just kind of have to spell everything out. It's the question that I think if it showed up on a midterm, everybody would start freaking out and just not even write anything down. But of course, the moment you write something down, you're like, oh yes, that isn't too bad. Okay, so any questions about that? That's our last example for now of straight quotients. Quotients will still come up when we talk about the isomorphism theorems, but this is our last example of straight quotients here. So is everyone's fine with that? Okay. All right, so let's do the first isomorphism theorem. And now there are three. Okay, there are three isomorphism theorems, first, second, and third. The second isomorphism is useless. In fact, we've kind of already seen it, but it's dumb. Okay, I'm not even going to talk about it. And you can look at them if you want. I don't think there was any plan to talk about it. In fact, you probably more or less used the second isomorphism theorem in one form or another on your previous quiz. So it's dumb and it doesn't show up anywhere. First isomorphism theorem is one of the most important theorems you'll ever see in your life. Okay, so I say this, I'm about to write down what the first isomorphism theorem is. This theorem is crazy and super, super important. Okay, it has a name, and its name is the first isomorphism theorem, right? So that kind of tells you it's an important theorem, right? And is it the first because it was the first we came up with? Is it the first because it's the most important? Who knows? Okay, so the isomorphism theorems. The first theorem, which is the first isomorphism theorem, and this is a pretty universal name. Everyone in the world calls this the first isomorphism theorem. If n is a normal subgroup of G, if phi maps G to G prime is a group homomorphism, not an isomorphism, is a group homomorphism, then G mod its kernel is isomorphic to the image. Okay. So if I give you a group homomorphism, and this is what I was saying. Remember when I was talking earlier about this fact that every normal subgroup would arise as the kernel of a group homomorphism, but you didn't necessarily have to use the quotient map. This is an example of, well, listen, the quotient map's always surjective. We're not guaranteed that every group homomorphism is surjective. So it's absolutely possible that you'll have your normal subgroup arise as the kernel of a non-surjective homomorphism. Now, often when we use the first isomorphism theorem, we do look at where phi is surjective. That's kind of more important. In fact, why don't we include it? So in particular, if phi is surjective, right, that means its image is everything. Then G prime is isomorphic to G mod the kernel of phi. Okay. So in particular, phi is surjective, then this is true. This is basically one of the most important theorems that we're going to learn this year. It's so crazy important. Like, when in doubt about showing that two things are isomorphic, use the first isomorphism theorem. Okay. So let's see. So I'm just kind of quickly talk about the proof. I don't think, should we do it all? In fact, let me see if I can think about why this would be true. So again, if you think about the kernel of phi, let me just kind of give an intuition for why this is true. If you think about the kernel of phi, basically the kernel keeps track of how many to one your function is, right? So if your function like maps three things to one, right? So it's not a one-to-one function. Well, if it's one-to-one, the kernel is trivial. If it's 2-to-1, right, then your kernel keeps track of that for every element. If it's 3-to-1 and so on and so forth. And so when you quotient out by the kernel of phi, what you're saying is that all the elements which have the same image are going to shrink down and become the same thing, if that makes sense, right? Remember, when we showed that a map was injective, or a group homomorphism is injective if and only if the kernel is trivial, right? And so the way that you effectively prove this is you say if phi of x is equal to phi of y, right? If they have the same image, then xy inverse is in the kernel, i.e. the kernel is keeping track of which elements map to the same thing. And so if I quotient out by the kernel, what I'm doing is I'm saying that all the elements which have the same image are going to go into a single point. And that's why you isomorphically get your image set, right? Because you've taken all of your redundancies, and when you quotient out by the kernel, you've shrunk them all down to a single point, okay? That's the idea. That's why that works. And so the isomorphism here is the very natural, right? It's exactly what you want to do. So you're going to say define, let's maybe call it psi. We want to show they're isomorphic, so we need an isomorphism to G prime. And the way that I'm going to do this is I'm going to take the equivalence class of G, and I'm going to map it to phi of G. Okay? So there's a bunch of stuff, or sorry, I guess I should say the image of phi here, because I'm not proving the special case. So there's a lot to keep track of what's going on here, right? There's a homomorphism phi, there's psi, which is going to be a group isomorphism. There's a lot of functions going on here. So just be sure that you're carefully keeping track of what is what, okay? Now, because we're defining a map on equivalence classes, we have to check the map is well defined, right? Anytime you define a function on a set of equivalence classes, you have to check that your map is well defined. Okay, so first thing, well defined. Right, so let's suppose the equivalence class of G is equal to the equivalence class of H. That is G inverse H is in the kernel of phi, right? So G inverse H is equal to K for some K in the kernel of phi. And again, this is what I was saying. where, if you have 2 points that are going to map to the same thing, the kernel keeps track of that, right? Okay, so suppose G is equal to H. So we want to show that psi of G is equal to psi of H. So thus psi of G, right, is equal to phi of G by definition. Now G is equal to what? HK inverse? Phi of HK inverse, right? Using this. That's equal to phi of H, phi of K inverse. But K is in the kernel of phi, right? So in particular, it maps to the identity. And the identity inverse is still the identity. So that gives us phi of H. And that's exactly what psi of the equivalence class of H is, right? So the map is well defined. And precisely the same proof shows that it's injective. In fact, or we can just kind of do it in a different way. So note that the kernel of psi is going to be the set of equivalence classes G such that phi of G, well, maybe let me say psi of the equivalence class of G is equal to phi of G has to be the identity of G prime, right? And what is that? That's precisely going to correspond to the elements of little g, such that G is in the kernel of phi, right? So this is the equivalence classes such that G is in the kernel of phi. But the kernel of phi is the identity element here. Namely, the only thing which survives is precisely the identity equivalence class, right? So the kernel is trivial, therefore our map is injective. Surjective is trivial in the sense that there's an obvious thing to choose, right? So let phi of G be an element of the image of phi. Note that psi of the equivalence class of G is equal to phi of G. So psi is surjective. Okay, so we've proven it's bijective, well-defined. The only thing left is that it's a homomorphism, but that's trivial as well. So the only really tricky thing here is injectivity and well-definedness. Homomorphism, right? Psi of GH is phi of GH. Phi is itself a homomorphism. That's phi of G, phi of H, and that's exactly psi G, psi H. All right, so psi is an isomorphism. And that tells us that G mod the kernel of phi is isomorphic to its image, like so. Okay. Super awesome theorem. So good. So good. This is the good stuff. Again, I really can't emphasize enough that this is a great thing to try and think about, is really to have a good intuitive understanding of what the first isomorphism theorem is saying, right? Again, if you have multiple things mapped to the same point in the image, then when you quotient out by the kernel, you collapse all of those things into a single point. Okay, that's really the beautiful thing here and the thing that you want to take away. Now, let me show you how we can use this. Okay, so example. So have we ever shown to you that the unit circle is a group? Have you seen this before at some point? I can't remember if it was done in the book, but that the unit circle is actually a group. Is that familiar? There's a couple of ways that you can do this. You could, for example, do this. You could say write S1 as the set of complex numbers whose modulus is 1, right? And then you would define the group operation so e to the I theta times e to the I psi is e to the I theta plus psi, right? So that's a group operation. Another thing that you could do is you could write, this is the collection of 2x2 matrices. Theta in 0 to 2 pi. Okay, and now this is a natural subgroup of the invertible 2x2 matrices. These are just the linear transformations that are rotation, right? These are the rotation matrices. You've probably seen this in 223, right? So if you identify the points in a circle with how much you've rotated them, this is now just a group under matrix multiplication. Under matrix multiplication. Okay, these are both ways of thinking about S1. They're very clearly isomorphic, right? And the way that you would see that these are the same thing is you would take e to the I theta and you would map it to sine theta, cos theta. Actually, do I have cosine sine? Oh, shoot, I think I have cosine sine backwards. Cos, sine, sine, cos, right? So you take e to the I theta, you'd map it to cos theta, sine theta, negative sine theta, cos theta, right? And that's no problem. That's very easy to prove that that map is bijective. Okay, so S1 is a group. What was the point of this? I haven't used the first isomorphism theorem. So note, this one's really cool. So let's define a homomorphism from R to S1. Maybe let me write it as the complex numbers. So what I'm going to do is I'm going to take theta and I'm going to map it to e to the I theta, like that, right? So you give me a real number, and that I'm going to map that to just e to the power of I theta. This is a group homomorphism, right? And again, implicitly, if we haven't said what the group operation is on R, it's addition, right? So this is clearly a group homomorphism. Right? Because what? We get phi theta 1. Well, here, let me write that on a new line. So we get phi theta 1 plus theta 2 is e to the I theta 1 plus theta 2. And here we're using like the Moivre's theorem, right? Phi of theta 1, phi of theta 2, right? So it's a homomorphism. Its kernel, what is its kernel? Can anyone see what the kernel is? Oh, actually, you know what? Let me do 2 pi, just to make this a little bit easier. So let's do 2 pi I theta, and just put a 2 pi in front of everything. 2 pi I theta 2. Still, right, it doesn't change. If you just increase the rate of rotation, it doesn't make a difference. Note that the kernel of phi, okay, so what is it? It's going to be all the collection of numbers theta such that e to the 2 pi I theta is the identity, is 1. And if you think about that, right, if you remember a little bit about your complex numbers, when is this going to be equal to 1? Well, precisely when theta is an integer, right? Therefore, by the first isomorphism theorem, by the fit, R mod Z is isomorphic to S1. Right? Beautiful, beautiful. Okay, and the geometric picture of this is so beautifully clear, right? If you think about what's going on here geometrically, what you're saying is, take the real line. So you've got this whole real line here, right? That's like 0, -1, -2, 1, 2, etc. And then the equivalence relation defined on R mod Z, right? So again, if you want to think about things as quotients, you can, or you can think about them as an equivalence relation. And the equivalence relation says that, right, A is related to B if A minus B is in Z, right? So that means that if I choose a number here, like 3/4, then the equivalence class of this is 1 3/4, right? 2 3/4, right? -1/4, -1 1/4, right? And so on and so forth. So you can see that you choose a point, let's say between 0 and 1. You choose a point between 0 and 1, and then the equivalence class just occurs by moving over, looking at all the integer sums of that point, right? So you just go at 3/4, you go over 0.1, you go over another 0.1, another 0.1. That's the equivalence class. So what that means you can do is, if you've got a good understanding and intuition for quotient groups, what that says is you can just say, look, you know how like when we do the integers mod n, we say there's a natural set of equivalence classes. So if you're looking at Z3, we usually choose 0, 1, and 2. You could choose 3, 4, and 5 if you wanted to, but we usually do 0, 1, and 2. So what I'm going to do is I'm going to say take 0, 1 to be the representatives of our equivalence classes. Our equivalence classes. Okay, but it's not the interval 0, 1. Why? Because look at what happens. If you walk along the line in this direction, right? When you get to the point 1, what happens? You go back to 0, right? So you're walking from 0 to 1, but then when you hit 1, it's like there's a portal there and you get sent right back to 0, right? Because that's the beginning of the next set of representatives of the equivalence relation. Very similar to what we do when we do Zn, right? You would do in Z3, you go 0, 1, 2, and then the next one is 0 again, right? You get sent back to the beginning. So when we do this, we have 0 to 1, but 1 must somehow loop back to 0. But 1 loops back to 0, right? So if you were to think about if the interval 0, 1 were a piece of string and you needed 1 to loop back to 0, you would glue that 1 onto the 0, and what you're left over with is precisely a circle. So gluing 1 to 0 gives a circle, S1. Right? So I love that. So this is the sort of geometry, I think I mentioned at the beginning of the class, the group theory that I do is not very discrete, right? I don't tend to do discrete group theory. I do Lie groups and play around with these sorts of things. And so this is the sort of group theory that I do, is this sort of stuff. And I think that's beautiful because there's so much geometry there and you can really see the geometry and see what's happening, instead of just when you quotient by like discrete things, often you don't have a good visual picture of what's happening. You just have to appeal to an algebraic intuition. With these sorts of things, there's a really nice level of, geometric intuition as well as the algebraic intuition. Okay, so I think that's cool. Let's do. Okay, so I'm skipping the second. Let's do the third isomorphism theorem. This is sometimes called the Tower Theorem. Okay. And the statement of this theorem, I'm actually going to state it as a slightly stronger version than what's in the book. So my statement goes as follows. It's almost the same, but I have a slightly stronger statement. So suppose H is a normal subgroup of G, and N is a subgroup of G such that H is contained in N is contained in G. Okay, so then N mod H is normal in G mod H if and only if N is normal in G. And in that case, G mod H mod N mod H is isomorphic to G mod N. Okay, and so this is cool because these aren't fractions, and we know that they're not fractions. But if you think about that thing on the left-hand side like a fraction, then it's almost as if the H's cancel, right? Like if you really were to treat that thing on the left-hand side as a fraction, write it as G over H times H over N, right? Because if you divide by a fraction, you take its reciprocal. So you have G over H times H over N. And it's like the H's cancel, and just what you're left over with is G over N. So it says that when you quotient, you actually, and by normal stuff, right? When you quotient by normal stuff, exactly what you want to be true is true. So that's a cool thing. And it's sometimes called the Tower Theorem because what this really tells you is that you have this correspondence between the groups N. So if you look at N here, right, N occurs between G and H. And the subgroups between H and G perfectly correspond to the subgroups between G mod H and, or let's say the subgroups of G mod H, right, of the quotient group of H and G. So you get this perfect correspondence between these subgroups and the subgroups of this thing, right? So it's sometimes called the Tower Theorem for that reason. Okay, again, I'm going to take a slightly different approach than what I think Ali is doing. So notably, the textbook does not have a proof of this, but I think, if we look at Ali's lecture notes, he's planning on doing this proof in his lecture. Now, I think he's going to do it by hand. And there's nothing wrong with that. You can totally do it by hand. Again, I want to give you a slightly different perspective here. So let me give you a slightly different proof. And so what I'm going to say is let's take the natural quotient map. I guess which direction are we proving, right? So which I'm going to actually prove the backwards direction first. So let's say let pi be the map from G to G mod N, be the quotient map. Right? The kernel of this map is N. And H is in the kernel of phi, right? It's in N. Thus define the following map, which I'm going to call pi hat, from G mod H into G mod N. And the way that it's going to go is it's going to take the equivalence class of G in H, and we're going to map it to, well, what you think we're going to map it to, right? The equivalence class of G in N. Okay. Okay, so again, we have to check that this is well defined. Actually, am I proving the, oh yeah, no, I am proving that direction, right? So I'm assuming that N is normal. Okay, so this is well defined. And the reason that it's well defined, so suppose that the equivalence class of G in H is the equivalence class of G prime in H, right? So what does that mean? Let me just double check what I want to say here. Right. So thus, okay. So thus G inverse G prime is in H, but H is in N, right? And so since G inverse G prime is in N, that tells us that G inverse, or sorry, that tells us that G n is equal to G prime n, or the equivalence class of G in n is equal to the equivalence class of G prime in n, right? So we get pi hat of G in H is equal to pi of G in n is equal to pi of G prime in n, which is pi hat of G prime in n, like that. Okay, so this map is well defined. It's clearly a homomorphism. Okay, you can double check it algebraically if you want, but look at how it's defined. It maps to pi of Gn, and we know pi is a homomorphism. So this is just immediately a homomorphism, right? Again, if you really want to spell it out algebraically, you can. So it's clearly a homomorphism, and its kernel so the kernel of pi hat is the collection of what? So again, here's pi hat. Let's take a look at this. Let's be careful. So it is going to be the collection of, oops, not yellow. It is going to be the collection of G's in H such that pi hat is the identity. In Gn, right, which is just n. So namely, what we're saying here is that it is the collection of, again, let's translate this to cosets now. So it's going to be the GHs such that Gn is equal to n, right? So again, that's if we translate what this means into cosets, and that's precisely n over h, right? It is precisely the cosets of h in n, right? Because G has to be in little n, and we're taking cosets over h. So it's in n mod h. So by the first isomorphism theorem, or well, actually, we don't want to prove the equivalency yet, the isomorphism yet, but this shows that n mod h is the kernel, therefore it's normal. Thus, n mod h is normal in G mod h, right? So that proves that direction. And then in the forward direction, so what are we doing again? So we assumed that n was normal here. We showed that n mod h is normal. So now let's assume n mod h is normal. Mod h is normal. Let's maybe just write that in symbols. Is normal in G mod h, right? Okay, so yeah, so what we're going to do is consider the map phi. We're going to go from G into, let me just double check here, G mod h into G mod h mod n mod h. Right, which again I can do because I assume that n mod h is normal in G mod h, so I know that that is well defined. And if you think about what this does, so it takes an element G and then maps it to GH and then maps it to GH n mod h, like that, right? Which is a little bit weird, but you're like, okay, that's fine, that makes sense. And the kernel of this map is n. Right, so now we get that the kernel of phi is the collection of G's in G's such that GH, oops, that's an n, GH n mod h is equal to n mod h, right? And that's precisely the statement that GH is in NH. So G in G such that GH is in n mod h. So again, n mod h is the collection of cosets where the number in front is in n, right? So if we need GH to be in N mod H, that means that G is in N. So this is the collection of G's and G's, such that G is in N. So that's equal to N. Thus, N is normal in G. So now I've proven the if and only if, and then any of the first isomorphism theorems give me the result, right? So using the first isomorphism theorem, IT on either pi hat or phi gives G mod H mod N mod H is isomorphic to G mod N. Right, and we're done. Okay. So yeah, hopefully that helps out. Now, there aren't a lot of good examples of where you would use the third isomorphism theorem. It comes up a couple of times. Certainly it comes up more than the second isomorphism theorem. The second isomorphism theorem doesn't even generalize well to more general abstract algebraic things. Though third isomorphism theorem does generalize well. For example, there is a third isomorphism theorem of vector spaces. Okay, so if you are familiar with quotients of vector spaces, you can prove this theorem for vector spaces as well. Turns out to be exactly the same. And in fact, I don't know if anyone would have seen it. The first isomorphism theorem is also true of vector spaces, right? If you give me a linear transformation, let's go back and let's look at the first isomorphism theorem. You can state this thing for vector spaces. You can say, listen, if T is a linear map from V to V prime, then T mod the kernel of T, or sorry, then V mod the kernel of T is isomorphic to T prime. In fact, that's rank nullity. That is the rank nullity theorem in a nutshell, right? Because you can actually show the dimension of the quotient space is the difference of the dimensions, right? The difference of V mod W is the dimension of V minus the dimension of W. So you can get rank nullity from the first isomorphism theorem. So both of those theorems apply even in vector spaces, which is a cool thing. So if you've never played around with that before, try it as well. Just play, if you want, with the additive structure of vector spaces. It might be a good place for you to mess around with some stuff. And yeah, you'll get to see that these work. Okay, so spend a little bit of time playing with quotients. Quotients are definitely, they're tough the first time that you see them. I don't doubt that there's a fair amount of confusion here, but give that a shot and kind of see how that goes. Okay, we're at office hours now, so of course I'm going to hang around and answer any questions that you have, but thank you for coming, everyone. Again, when you go back and you watch this video, if you have any questions, throw them on Piazza and I'll do my best to answer them quickly, just in case there are any questions here. This is tough stuff. I know it is. Okay. All right, everyone. So thanks for coming in. We'll see you on Thursday if you're not hanging out.
Hello.
Hey.
Can you scroll down a bit?
Sure.
To the